Hello, welcome to Mastering Statistics. We're going to do another problem in the right-tail test, hypothesis testing with two variances, but instead of a word problem, I'm going to just write the raw information down because what you'll find is that when you read enough of these word problems, they're all the same. So I want to save a little bit of time after I gave you a little practice with the word problem. I just want to give you the raw data and so that you can kind of crank through a bunch of these things and learn something. So what you might be given, for instance, is that n sub 1 is 20, right? And s sub 1 squared is 10.453, and we'll talk about all this in a second. You'll also be given that n sub 2 is 23, and that s sub 2 squared is 3.199, okay? And you might also be given that the alternate hypothesis is sigma 1 squared greater than sigma 2 squared. And you might also be given that alpha is 0.10. Essentially, this is all of the information that you pull out of any of these problems. You just have to read the problem to get to it. And I'm just kind of giving it to you here because I want to crank through one a little faster and just kind of get through the mechanics of it. So this could be anything, right? You have two populations, population 1, population 2. This could be the age of death or something at, in different continents, right? So we sample 20 people from, North America and, 23 people from Australia, and we get a variance. We get numbers, we get raw numbers, that maybe the age that they died or something like this. But from those raw numbers, we calculate the variance coming from population 1. In other words, how spread is the data? How tightly packed is the data, right? And we get the variance coming from population 2, which could be Australia. If this were about the age of death, then what we would figure out is the people from North America has a wider dispersion or wider variance in the age that they actually die than the people from Australia. They seem to be a little more tightly compacted around the average age of death in Australia than maybe in North America. This is totally made up. This could be the length of cans coming off of an assembly line or anything. But what you're figuring out is you sample 20 from population 1 and 23 from population 2. You get a higher variance from population 1 than population 2, and you're given that the alternate hypothesis is that we're looking at the population variance being greater than the population variance from population 2. So the alternate in the case of the age of death would be, or the life expectancy, I guess is the right way to put it, is that the variance in the life expectancy from people in North America is greater than the variance in life expectancy from the entire population. So whereas the hypothesis, alternate hypothesis, deals with everybody in the population, our data only deals with the sample, so that's why we use S. And we're testing at a level of significance of 0.1, which is only 90%. So to crank through this stuff, the first thing you need to do is write down the claim. The claim was already given to you. The claim was that the alternate hypothesis was that sigma 1 squared, the variance from population 1, was greater than the variance population 2. It doesn't matter what we're talking about, but it's greater. And because of this arrow going to the right, we know, because the claim has a right arrow, it's a right tail test. It's a right tail test. Now, once we have the claim written down, we can go and write the null hypothesis, which is basically the exact mathematical opposite of what the claim is. So you write down exactly the same thing as far as the symbols go. The variance of population 1, you're comparing to population 2, but now you flip the arrow and put an equal sign because that's going to cover all possible other cases. The claim is that the life expectancy variance in life expectancy is greater in population 1, population 2. And the null hypothesis must be the accepted standard view, which is that they're either equal or that population 1 has a smaller variance. Okay? Clearly, the data looks like, at first glance, that population 1 doesn't have a higher variance, but we need to test it at the current level of confidence. So the first thing you need to do is, and again, you can do it in any order you want to, but let's go ahead and figure out what the rejection region is. So I'll write down rejection region. Basically the boundary there. And to do that, remember that the test statistic that we're going to eventually use is S1 squared over S2 squared, right? So from this, we can calculate the degree of freedom of the numerator is equal to what? We sample 20 people from population 1, so the degree of freedom is going to be, for this guy, 20 minus 1 is 19. And then we can calculate the degree of freedom for the denominator. And we calculated, or we sampled 23 people from this guy, so it's going to be 23 minus 1